Hello, my name is Christos Evripidou, and I am a senior software consultant at Rapita Systems, and I'm the technical lead of our Multicore timing analysis projects. Today I will be presenting our demo of the Darknet YOLO application. As you can see, the application runs on an NVIDIA Jetson TX2 board, which has 4 ARM A57 cores and 2 Denver cores, 8 GB of DDR4 RAM, and its GPU features 256 CUDA cores. The application itself is called Darknet YOLO v3. It's an open source artificial neural network which is written in C and CUDA. It does object detection and classification using the Darknet framework, which is an implementation of a neural network, and it's available on GitHub. The application itself it starts off by loading the neural network in memory, and then it processes the video feed frame by frame, as you can see on screen, and for every frame it uses the neural network, which executes on the GPU to detect objects, calculate the bounding boxes around these boxes, draw the output, and then proceed to read the next frame and until the feed is finished. Here on screen we can see the application running on a set of dashboard camera feeds, and we can see that our application runs at about 13 frames per second, with no contention on the hardware resources. Here we have a simple user interface where we can introduce contention on specific resources to see the impact this has on the frame rate. So if I were to introduce a contention on the main memory, we can see that the frame rate drops down to about 10. This is because this hinders the communication between the CPU and the GPU, therefore the frames are processed a bit slower, and we can kill the contenders and actually see the frame rate restored to the 13 frames that it previously was. So as I've mentioned, there is communication between the CPU and the GPU, therefore a bus contender would have more impact than a memory contender, since this is specifically tailored to hinder the communication. So if I were to start the bus contenders, we can now see that the frames per second is consistently below 10. Now, since this is a this can be used in a safety critical application, for example self-driving cars, obviously if the frames per second drop too much, then we can potentially have delayed responses that would impact the safety of the vehicle. This user interface allows us to observe in a simple way how different kinds of contention may affect an application. Now, one of the challenges is that different applications can get affected by different kinds of contention by various amounts. In this case, we can investigate the caches on the board. So here we can see that when there is contention on the level 1 instruction cache, there is no impact in the timing behavior of the application. Similar with the level 1 data cache, we can see no impact. Then when we introduce level 2 cache contention, we can see a very small amount of interference, which drops our frame rate from approximately 13 to about 11 or 12. Then when we move the contention to main memory, there is even slightly more of a drop to about 10 frames per second. And the worst contention in our list here is having the bus contention, which drops the frame rate to under 10 frames per second. Of course, we can also mix and match different kinds and levels of contention. So we can see that when we mix bus and memory contenders, we also drop the frame rate to under 10. We know that this is the cause of the frame rate drop, because as soon as the contenders are killed, the frame rate is indeed restored.